Hi, and welcome to our next episode of our series of webinars. So today I'm going to talk about the topic how to embed a robotic system into a simulation, so an embedded simulation with Principia, with our kernel. And I'm going to discuss a use case, namely the one together with a company named Sirob. All right, so let's see. What is our agenda today? So first, I'll introduce myself and the company, then our app Principia, but I'll keep it really short today, and also the multi-body dynamics background. The main focus today is on the use case with the company Sirob. And after these points, we will have some time to discuss your questions if there are any of them. All right, so let's start. The company Principia MBS was founded early 2023, so we are about 1 year old. We are a solution provider for design validation tools that are integrated into CAE platforms. Our competences are in designing or implementing numerical solvers for modeling dynamical systems and algorithms, all of them for doing dynamical analysis. But we've also have experience in UI UX design and web development, as we are a cloud-native solution, and within a browser, we of course have some knowledge in web development. To my person, my name is Stefan. I'm the CEO of the company. I have an educational background of technical college, then started with mechanical engineering studies, and then during my time at the research group for multi-body dynamics, I did my PhD in mechanics at the Technical University of Vienna. My competences are in the field of engineering and CAD design. I have knowledge in solid mechanics and simulation tools in general, but very specific in the field of multi-body dynamics, and I'm into method development, and also I did many projects in the area of software development. So the kernel of multi-body of Principia MBS is basically my baby. So I'm into software development too. So what is Principia? To introduce our product, it's the first cloud-native multi-body simulation app. So that's the thing you see here. We are right now integrated into the CAD tool Onshape. So what you see here is a screen of Onshape, so an assembly view, and in green, the green box, this is our app. So this is the region where we are active. So within an Onshape assembly, you can do multi-body system dynamics. So do the modeling, do the post-processing, the analysis of such models. So as I initially said, we are browser and web cloud-based. So that means this is our UI that really comes native in the browser. So a little bit about multi-body dynamics itself, because it's sometimes a bit confusing what is this about. So it's basically about motion analysis, and the term for it in research is multi-body dynamics, MBD, or multi-body system dynamics. It is all about studying the motion and the behavior of interconnected mechanical systems. We are into analyzing forces and interactions between bodies. We gain insights into the system behavior overall, and therefore can evaluate the performance or identify special issues like are there collisions, etc., etc. What is MBD not is, it is not finite element analysis. That means we are not into detailed structural analysis or computation of deformations and stresses. Most of the time there are inputs needed from MBD, so the loads for FEA are from MBD, but we are not into this detailed analysis. And we are also not into computational fluid dynamics. This means we are not investigating the flow of fluids, etc. So that's also some different area of simulation tools. So what are the typical tasks that can be done with MBD? So these are the main three tasks I just shown on this slide here. So it's first for function checking. That means you have an assembly, a system of interconnected bodies, and you want to check if motion is possible. So are there any collisions? Do my actuators have enough power or force, torque to move the system like I would like to have it? Or are there any other issues that may show up? This can be done with MBD. Then when it comes to forces and all the details that coming out of a multi-body dynamic simulation, one thing is that you can do scaling of parts, so standard parts and machine elements with the forces generated by multi-body analysis. So that means if you have any roller bearing, ball joint, etc., you can create forces, and with having the limits from the tables for the standard elements, you can decide whether to choose a smaller or a bigger element, or if it's already the right one. Of course, you can do also dimension your drives, your other force elements like hydraulic cylinders, etc. So that's all in this area of tasks of MBD. And last but not least, load generation. This was or is the main task of MBD, namely to generate realistic forces, inputs, so interface forces, in order to investigate the structural deformations and stresses with finite element analysis. So usually this is a two-step approach. You have your overall system, you simulate it with MBD and take out only the interface forces in order to load your solid bodies with it, and then you can do either strength analysis or fatigue analysis. So these are the three tasks that can be done. And today we look onto a very special tasks. Partially there were some similar tasks like I've described, but embedding the whole system is something different. So first of all, let's start with the company Sirob, who gave us the use case. So at this point, thank you, Johannes Biller, the founder of Sirob, to allow us to share this content with you. So what is the company Sirob doing? They are specialized in automation, so they have decades of expertise in commissioning within the automation sector. They emphasize on the development and application of mechatronic concepts at all, so not only robots. They have several innovative solution approaches when it comes to robots. So traditionally, robot and system controllers have been implemented on two different platforms. This results in, say, complex configurations. And Sirob did some pioneering work in this field in order to simplify this complex interrelationships through innovative solutions. So they collaborated with Autonox Robotics. They are a producer for such robotic systems, and they were involved in the development of the Autonox Robotics controller-independent robotic mechanics. So that means you can buy a robot from Autonox without any controller and implement your controller within your standard PLC. So Sirob was involved in this process from the initial concept to the product's readiness for series production. So that's about the company Sirob. So what was the problem? What you see here in this animation, you see a delta kinematic robot. So that was all about, so that was the initial idea. We started the project with the idea to simulate such a parallel kinematic or delta kinematic robot. But as these robots have some slender design, so you see these forearms, they are very thin, and these are fiber reinforced composites. So these tubes are not made out of metallic material, but of composites. So that means when you have some fast motion and some high dynamics, you probably get some vibrations due to this construction. And vibrations may lead to wear and tear in probably joints or any other interfaces. Of course, it can be problematic that they lead to imprecise positioning as there are vibrations, and if you do not compensate for them, you can have the case that positioning is imprecise, or due to this oscillations and therefore the compensating work of the motors of the drives, this may lead to increased power consumption. So this is one topic here that one could be interested just in simulating such a model or a system. Another topic here is one can use multi-body dynamics to generate the values for the torque required to follow a given trajectory. So if you are interested in picking a part from one place, then putting it to a second position, you can, with the given trajectory, you can of course create the torques that are needed from the servo drives, and then you can decide which side of the drive to choose. In this case, as I said, the autonomous robots, they are very modular, so you can not only define the kinematics, so the length of the arms, etc., but also you can choose the drives you want to apply onto the robot. So that's why it's important to know about the situation you are using it in, and also the forces, torques that are needed to do the job. So that means for generating these values or to decide which model to choose, this is also beneficial. And on top of this, so right now we've been in the area of just simulating such a model, but with embedding it into a control loop, we were able to optimize a controller. That means, as I said, there is no controller shipped with the robotic system. This has to be implemented in the PLC. And also these parameters are not shipped with the robotic system. So the standard PID control parameters, they are not shipped with it. So that means you have to select them or adjust them. And with using a simulation, you can do this prior to going into the field or when you are commissioning the system. So you can already do this setting of parameters on the computer with the simulation model. So as this robot is highly individual and adaptable to users' needs, this is always a very, individual task for one project. You can tune these controller parameters to your needs. And in the field, you only have to fine-tune this because of several issues like parameters or influences of different environments, etc. All right, so this is the problem. So we were looking for a simulation and embedding this simulation into a controller, which can be used to tune the controller parameters. So the solution now was to build the model kinematics and dynamics with Principia MBS. Therefore, as the robot is not designed in Onshape, it was necessary to import step geometry and also define the full kinematics there. So that means add mate features, so the joints that are interconnecting the system. Of course, I forgot to define the materials because we, for the dynamic simulation, also need materials. And for the later use, to define forces and sensors, one has also to add mate connectors, so coordinate frames or some markers that are moving with the system to make life easier whilst modeling the dynamical system. And then, as I said, these slender forearms, they led to vibrations. That means they definitely have to be taken into account as a flexible structure. That means this cannot be done within the rigid body model of Principia MBS. So this was something to be done in an external FEA tool. So meshing, adding a standard header, that means a standard computation procedure to generate a substructure that can be used within our simulation kernel. And then finally, when everything's done, one can define things in Principia MBS. So add the servo drives as a force element, and also the TCP position to measure where the position of the tool center point is. At this point, I'd like to jump into in a live demo. I'd like to show you this model that was used in, let's see. This model was used. So this is the import coming from the Autonox website. So they publish all their designs on their websites as a step file. And also some details like the inertia of the arms, etc. That is all published. So what I did, I added the kinematics, so the made features, you see them here, so that it was possible to move the kinematics around. So as you see, kinematic solver within Onshape really works. I also did some configurations here, so that means I can, for example, define the arm positions. So that is one configuration I can do, or I can define the tool center point position. So that means I can change the initial configuration of my model. And once I've done this, I can start with, of course, finite element modeling. That's the thing I won't show today because it would take some time. So just as an information, this was done within Abacus and then exporting it to a substructure, as I said. But nothing more than exporting the geometry shell here from the CAD tool, then importing this meshing, and then generating the substructure. Good. And when this is done, one can jump into the Principia app. So Principia, as I already said, is implemented as a side panel app in the Onshape assembly view. So once the Principia app is opened, all the details from the Onshape assembly is loaded. So that means all the parts, so the bodies with their inertial information. So the inertia information, so mass and in moments of inertia, principal axis of inertia. So this is all automatically loaded. Then we have the section of constraints. So that means all the Onshape made connectors, Onshape made features are imported and interpreted for the use within the Principia engine. So this is the kinematic model that is loaded here. And then, as I said, we have to define some additional things like the servo motors, because servo motors are not part of the kinematics model in Onshape. In this case, we have 3 servo motors. This is a predefined element in our app, so you can choose this. All you have to do is select action and reaction made connector. So that means where should the action torque act? So this is in this case this upper arm, and the reaction. In this case, the reaction is on the upper arm, and the action is onto this platform. So as we missed to model the motors directly because they're not needed here, they're just static. Torque is applied onto this platform. Then one has to define in which orientation, or what is the axis orientation for the torque to be applied. In this case, it was the Z-axis, because the mate connectors that are used here are those of the revolute constraint or the revolute mate in Onshape, and here the free degree of freedom, so the rotational degree of freedom, is always the Z-axis. And then what's left is to define the maximum torque that can be gained from the servo drive. In this case, it's just a setting of 100 Newton meter. That's of course a very large value, but this just means we do not want to have a limit in the force. The internal controller of Principia should just use the torque needed to perform the motion. And then we have to define an end position. In this case, the servo drive, the implemented servo drive, always drives from one position, so from the current position, incremental to a second position, in this case in the units of the angle, in this case degrees, so 45 degree, and then the motion duration, so how long should it take to move from 0 to 45 degree. And this is done for all three servo motors. And then we have one thing left, define the sensor. So in this case, the tool center point position, this is just a displacement sensor that measures two mate connectors. So there's one mate connector that is defined here. So that's the mate connector used, and that measures the current position of the tool center. And one thing we can do right now is start a simulation here in the Principia app and monitor the simulation. Shouldn't take too long. And then we have all the insights I just talked about, the torque needed, and if the motion really is done like I've designed it. So this is obviously 45 degree motion here, and the other arms are in standstill, so they are fixed. And the torque needed can also be read here. So that means in this case, we need 16 Newton meter to drive this motion. But that was not the main task of the project. It was just one side project here to just simulate the system and gain or get the information about torques needed. More of interest was the simulation embedded into the control loop. So let's jump into the presentation again. So what is needed then? Just to clarify this is nothing that can be done with the current version of Principia that is online. It's just in our dev version. So one can then export the model. And in my case, I used Scilab, so something like MATLAB, but it's a free tool. Alternatively, one could also use Python. So we have both APIs. And in this case, I used Scilab to implement the controller itself and to embed this model of the robot into this control loop. So export it. In this case, it's a JSON export, and then load this model via our application programming interface, so the API, and access the model there. The model there can not only be read out, but also used for incremental solving. That means you define a small time step size that is simulated, then you get all the informations, the readings out of the model, do something with it, in this case, define the control law, and then compute new inputs for the model, and then simulate one incremental step again. So all to be done now is to implement a PID control. So in this screenshot, you see the input I got from the company. So that's the controller that is used within the PLC. So it's a PID control that is has several levels. So first, there's a position controller that drives the velocity controller, so the angular velocity controller. And this angular velocity controller drives the torque controller. And this was implemented in the Sirob script, as I just said. But prior to this, to clarify this one, so this M here stands for the motor. That is really the one that is driven in the real case from the PLC. We, of course, have to get rid of this real system, like you see in the picture, and exchange this with our simulation model. So what you see here is the main control loop. So with the API functions, you can read out measure values or sensor values from the model. Then, so this is done in these lines. So you just if you have a real sensor on your mechanical system, you can just read it out via the API. Then you can apply the control law. In this case, it's all hidden behind this function compute torque. So here, all the 3 PID controls and also the inverse kinematic model for this delta robot is all in this compute torques. But to get an overview, this is just a function to compute 3 values for the torque for the upcoming time interval. And then this torque is loaded, or there's some smoothing, of course, not to have jumps in the torque, because then in this case, as I said, it's a flexible structure involved, and always then when you have flexible structures, you should avoid to have jumps in the torque. That's why there is also a smoothing function in between. And once this is done, it's just one call in this last line here. It's solve the next time interval with the principia kernel. So one has to define an update rate, or an interval, a small interval. Usually for the PLC controls, it's 1 milliseconds, like in the real case. We've also chosen this one here. So compute the next 1 millisecond. And after this 1 millisecond, compute or evaluate the control law again, and then drive your system. Of course, Principia writes all the outputs that are usually written and that one already knows from the output in our app in Onshape. So that means you can, of course, post-process any quantity you like. So not only the animation after the simulation, but also all the interface forces, all other positions and forces. So that's all written, in this case, into a file and not into the database, but it's something that can be loaded and then shown again in our interface. So, all right, what are the results of this approach? So what you see here is first, it's the operation of the robotic system. In this picture, you see a bit more, so also the overall surrounding and the tool that was mounted onto the tool center point. So it was a picking operation from one belt to another belt. And what can be done with just simulation is, first of all, using a motion, so a prescribed motion onto the tool center position to move apart from one to another position. And with this approach, you already get trajectories for the target angles. So you define the positions in Cartesian coordinates on the tool center point, move apart from A to B, and get the angles for all the 3 drives here. So inverse kinematics is done automatically without using any formula to be computed. Then when one applies the PID control, you can retrieve all the drive torques that are needed. So not only the torques we've seen in the Onshape Principia app with a prescribed motion there, but using the real PID control, including all the imperfections, say, of the torque signal. So you can really have a look into the yeah, the torques that would be observed when measuring them in the real system. That's the thing from simulation. With this PID output, you can check for operability. That means, are there any peak loads in the drive? So will the drive be powerful enough, or should there be should you choose another drive? And of course, are there any vibrations with the current setup? That could be of interest for different things. If it's the surrounding does not allow to introduce any vibrations, or to the support of the robot cannot withstand these vibrations, this should be something to be avoided. So that means vibrations can also be checked here. And the most important thing here in this project, one of the outcomes was one can do offline optimization of controller parameters. Offline should mean here not in the field, but in the simulation, prior to ordering any part, only in the virtual case. So what we've done here is we simulated the current status. So that was the thing, that was the initial setup, how such a robot was shipped to the site. And as you see, this signal shows the torque in Newton meters for one picking operation from the simulation. So it's a simulation result. And you see that it's really that there are high peaks and there's a lot of oscillation. And just to have one iteration, and we did many more, but one iteration was to change a parameter of the PID control, in this case, the I part, so the integrational part. It was, I think, doubled in this case, and this is the outcome. So just to compare, very large oscillations, and with the improved controller setting, these oscillations, of course, they are not completely flattened, because it's a PID control. One could also do further improvement, but just to show what's the main outcome, it is possible to predict all these oscillations from a control by having all the details of inertias, plus the flexibility, plus the actual PID implementation, all in the virtual space. That's pretty much it of today's webinar. So that means the takeaway of today should be multi-body dynamics or motion analysis is something that can be used for these three tasks I just introduced. So classical forward simulation, but it's also something that can be used to generate a simulation model, so a black box model, like just in this picture. So that can be used in any other domain, or for defining controllers, or designing an overall system. It's also something that can be embedded, and we at Principia, we can do this. As I said, it's nothing that can be done with the current app that is online and Onshape. But if you have any task like this, don't hesitate to contact us. This is something where we see the future of simulation, to also embed it in other simulation fields. So all of you that haven't checked our app right now, what are the next steps to your trial subscription? We are listed in the Onshape App Store. We are in the category simulation. And once you clicked on the subscribe button, you have your 30-day subscription there. And then you can play around with the model. Be aware, it only shows up in the assembly view. So you should see this icon here once you have clicked the subscribe button, and then the app opens up. First of all, you are asked to give permission to Principia, so that we are allowed to access your models via the API, because otherwise we don't have any data of your models. So that's why it's important to accept this. If you click deny, Principia won't work. Good. That's all for today. If there are any questions, I'm happy to answer them. Let's see if there are any questions in the chat. If this is not the case, please do not hesitate to reach out to us on any channel you like. So it could be LinkedIn, can be done via email, or any channel you like. We're more than happy to answer any question. And as I said, start modeling today and start your free trial. Yeah. Thank you for attending the webinar today, and see you soon.